So there were some mistakes regarding the automaton that was for decoding. Most of you had it correct. Actually, there are two states, the initial state and the half state. By definition, these two states must exist. So some of you said that there was no half state. Actually, there is half state. It exists always. Just in this case, there is no way to access it. So we had here that whenever we had a 0, it would move to the right. Whenever we had a 1, move to the right. And whenever we had a blank space, move to the right. Am I correct? Okay. So one mistake I saw repeatedly is that you said that there was no language associated to M, giving this is M, a machine. However, this is not correct because remember that even if you have this language, which is the empty language, this is a language. And from here, you had also other mistakes in cascade because if you say there's no language associated, therefore you cannot have complement of this language. And well, this is not true because you know that the complement of an empty set is the rest of the universe. And in this case, our universe is composed by 0, 1, and all the possible combinations of these symbols is given by sigma asterisk, which is any combinations of 0 and 1. And of course, we can build any a machine that accepts this. So you can see this is M1, and we could draw M2. And M2 would be any machine that moves to the right whenever it sees a 0 or a 1, and it will stop whenever it sees a blank space. That's it. So this machine accepts this language. So let's say language of M, let's correct this and say language of M1 is equal to empty, and language of M2 is equal to sigma asterisk. And because language of machine 1 is the complement of the language of machine 2, then we can have two different machines, one accepting the language and another one accepting the complement of language. Therefore, the language is decidable. Is decidable. So this is important. Some of you got a little bit mixed with L0. And remember that L0 is a particular language that consists of those, when we want to create a machine that rejects all those machines that cannot accept their own description. In this case, we don't deal with that. We don't, this problem doesn't have to do with L0. So don't try not to mix these concepts. L0 is just an example, of language, of a language that is not accepted by Turing machines. And therefore, it's not a phrase structure language. And however, if you consider the complement of L0, this is an example that is accepted by a Turing machine but is not decidable. Why? Because L0 is the complement of L0, and this we know that is not accepted. So we can say because its complement cannot be accepted by a Turing machine. So as you can see, for this problem, L0 shouldn't be involved. And here we have the two conditions that we need for a language to be decidable, that is accepted by a Turing machine, and also its complement is accepted by a Turing machine as well. So the answer, the correct answer for this problem is yes, Lm of M1 of this machine is decidable. And finally, you modified the machine. You modified in different ways, and most of them were correct, if not all of them. And well, you have the points corresponding to that. So I think this is the weakest point you had in your exams. Anyway, in general, well, I see that maybe some concepts need to review a little bit, but in general, I think you had a good score. And I'm just waiting for your last submission, which is the language, the Lisp implementations that should be not so complicated, I expect. And well, with that, we finish our evaluation. So if you have any questions regarding your evaluations, please let me know. Remember that there were some extra points before, so even if you had a low score in this last exam, well, don't trash everything to the garbage, because well, you can still have a decent note at the end, because also most of you have a lot of work during this class. So let me see, just there are some cases, I won't say names, however, just let me check with the people which is present here. If any of you is in risk, just to tell me to contact me. I don't know how I'm going to tell them without telling names, but let me see. Or maybe I can say your status currently, and I can say if it's okay or not okay. And if I don't say your name, maybe you can contact me afterwards. Let me see. Okay, so Abraham Larrazolo, okay, Arturo Sandoval. I cannot find you. So I need to, okay. Cristian Jaime, okay. Cristian Camilo, okay. I can give you a number. I can't give you a number right now because there's still some work pending, but at least I can say, don't worry. Of course, if you don't submit your last homework, well, maybe you should worry, but so far, if you do it properly, you won't have any problem. Cesar Macias, okay. Sara, okay. Dima, okay. Emilio Magaña, right? Okay. Erika, okay. Maraya, okay. Miguel Soto, okay. Oksana, okay. And Oscar Islas, okay. So just be sure to submit your last homework. I think everybody who is here is okay, fortunately. So please just submit your last homework and you'll be able to do properly this course. Well, at least you will pass. Any question regarding this? Well, of course, you will have a particular number, but I cannot know it now because there's still some work missing, right?
I have a question about the last homework.
Yes.
The last homework must be in Lisp or could be in Lisp?
could be in Lisp. You can use other language such as Haskell, as long as it's functional. And it should be mainly functional, because you may argue that you can do functional programming in Python, and maybe you are right, yeah, or even in C if you
In
use
Java.
don't do that. No, not in Java. Particularly not in Java. Well, theoretically you could, yes, but I strongly suggest you to choose a language that is functional.
For our own good.
Yeah, so I don't know, Scheme, Haskell, Ada, Lisp, Common Lisp. I think you can download Allegro Common Lisp easily from the internet. France Common Lisp, I think it has a paid version, and I think Common Lisp is already included in Linux. I don't know if you can tell me if I'm wrong.
No, it's just a package you can install. There are several packages.
Well, but it should be easy, just some sudo install CL or something like that.
It's not Windows, it's just one command. So
yeah, right. So it should be difficult for you. And also there are a lot of tutorials just to get started in Lisp. I mean, it's not that hard, so that's why I'm asking to program this. And these are simple programs. For example, the zero function just returns a 0, and all of them we know already, except maybe for the odd function, but you can figure it out easily. Or maybe the Fibonacci function, I think, is not so difficult for you. Okay, so well, you need to use a functional programming language. And also I am asking you to provide some screenshots, or maybe some way of saying a small report, not very detailed, where you say, these are the functions I programmed, I implemented them like this, and this, and when you execute it with these numbers, it has this output, and just like that. Okay, so more questions regarding. Welcome.
I found a Haskell online version. Can I use it?
It's okay. Yeah, if it works for you, it's okay. Just remember to take the screenshots, and of course, you need to submit the source code as well.
Thank you.
Haskell is nice because it has not so many parentheses. So if you feel more comfortable with that, it's okay as well. But I think it's almost the same, just parentheses and alignment. If you like alignment like in Python, well, then you may prefer that one. And that thing of alignment reminds me of Fortran 77, when you the meaning of your sentences had to do particularly with the column you started in. So if you start in a particular column, then it means it's a comment. If not, it's a loop or something. So I think we are going back to those times when we program in Python. But well, it's maybe just I'm taking the concept too far. Okay, so maybe we can get over with this subject of Turing machines. And I'd like to finish our subject of recursive functions by giving you some scenes of the last chapter. So it's okay. Can we go back to chapter number 4? Okay, so some scenes from last time. We had this diagram, and oh, sorry. And well, I have said this like too many times, and of course I know, I think Cesar asked me to upload the videos. I have them now, but I want to edit them because I don't want my mistakes to show up in the final version of YouTube. So that's why I take a little bit to upload it. Well, not big editing, but well, I promise to do it anyway. So we have some initial functions here. There are 3 functions only, and then we have these mechanisms of combination, composition, and primitive recursion. And with this, we are taken to the next level, which is called primitive recursive functions. let me remind you that all primitive recursive functions are total functions, meaning that we cannot define, or we cannot have undefined values for the domain of these functions. Then, if we want to go to the next level, we will grow up to this green circle by adding the minimalization mechanism. With this, we have all the power of partial recursive functions, which is in turn all computable functions. Some details here is that this inner ring, which is here, is composed by all the total functions, which are called also mu recursive functions. Last time I told you that you shouldn't be confused by this mu here and this mu mechanism, because they are unrelated. This is mu only to name these recursive functions that are total functions, but these functions do not use this mechanism, this minimalization mechanism. However, when we add this mechanism, then we have all the power to compute any function that we can imagine in the world. And also we saw last time that if we want to know how many computable functions are there in the universe or are possible, we concluded that these functions, or the number of these functions, was infinite but countable. And it's countable because we can map a number, a natural number, to each of these functions, because we can count how many functions we can have with two initial functions and one mechanism, two initial functions with another mechanism, two initial functions with another mechanism. And by this, we can count them. At every time we count them, we have finite sets. Of course, maybe they are very large. For example, if we consider those functions that are composed by 100 initial functions and 100 of these mechanisms, of course, there will be lots of functions, but this set would be finite. So because we can count them, and the same will happen with this because we are adding just another mechanism, then we will have an infinite number of partial recursive functions. However, this will be an infinite countable number. So let's write it here, infinite countable number. We have seen already this, but I want just to remind you forever so that you never forget, at least while you are still doing your masters. Okay, then if we want to know then how many different functions are there, what we did last time was to consider these functions, the number of functions that go from natural numbers to 0 or 1. Then we saw that taking them into account with a 1 was like including them in a set. When we assign a 0, it was equivalent to not including them in a set. So that the problem of counting how many functions reduces to knowing how many subsets do we have in the set of natural numbers. And since the beginning of this class, we saw that there was a function to create all possible subsets given a set. And this function is called power set. So the power set of the natural numbers will contain all possible subsets we can generate within the natural numbers. And of course, this is infinite. And to be more exact, the total number of subsets we can build on the power, we have the total number of elements we have in the power set of the natural numbers is 2 to the power of the size of n. So this number is much, much bigger than the natural numbers, meaning we cannot count how many subsets, or we cannot count this number of elements. Therefore, we have an uncountable, infinite uncountable number of functions, starting from natural numbers to 0 or 1, which for computability purposes is not good news, because it means there are a lot of functions here in gray that we cannot compute. Just by definition. So I wrote here the realm of non-computability because this is a dark zone and we don't know what this would imply. And it has lots of mathematical and philosophical implications. And well, this is what makes this class interesting. So this is the kernel of this subject, because well, the name of this is of this matter is theory of computation, and of course, the main purpose is to know what is computable and what is not. And we have seen two different ways to know this. One of them is by using Turing machines, and the other way is by using the theory of functions or recursive functions given by Alonzo Church. Therefore, computability theory is sometimes known as the Church-Turing theory. Church because of Alonzo Church, and Turing, of course, because of Turing. And they are not the only ones who defined what is computable and what is not. There are other authors that also go around this, and of course it has to do also with the Gödel theorem, as we saw before. So everything is highly related. At this point, then, we have reached, with everything that we were building during the course, we have reached the peak or the most important thing of this course. That's why I insist sometimes a lot about this. Okay, so as a final remark, today we will see how is this connected, not disconnected, no, how this is connected with the programming languages we have. So maybe I can ask you, what is the most powerful programming language you can think of? Maybe is it Lisp? Is it Haskell? Maybe is it, don't say Java, please, but maybe.
Assembler.
Don't say bad words here, please. This is a decent course. Or maybe Python, I don't know. So what do you think? What would you say is the most powerful programming language and why?
What do we call powerful language?
Yeah, that's a very good question. By power, we mean in terms of computing power, meaning that if they are, for example, Turing equivalent, or that we can compute all the partial recursive functions.
I think that are the high level language could be.
Yeah, yeah, and even not so high level. Maybe what about assembler language? Is it powerful enough or not?
Probably they're all the same.
Yes, in terms of what we have seen, yes. And today we will run a short demonstration on that. So how many basic components or how many basic instructions do you think the most basic, and I'm not speaking about basic, the language, but the most basic language, how many different instructions do you think it should have? Maybe you can think.
I really don't know assembler.
Well, maybe you can think of RISC computers, or which is a reduced instruction set, or maybe you can think of the simplest language you can think about, and just give me a number. I don't know, 10, 15, 20.
Oh, I know what are those operations. Write 0, write 1, move tape to the left, move tape to the right.
Maybe something like that. And yeah, of course, there are some implementation issues here that regarding the movement of elements from an array, load from memory into the main indexes, main registers, and put back into the registers. And maybe not taking that into account, well, I will give you the answer because we can keep speculating the rest of this class. So let me tell you, there is a very simple language that we will call the, well, it's called bare bones in this book. So this is the simplest language maybe we can think of without taking into account input and output, okay? So there is no print, there is no other things, but we have variable management. And we can have, for example, incr, which increases the value of this variable here. So this is one instruction. Another one is decr, which will decrement any variable, and we can say decker name. And finally, the third instruction will be given by while and var.
Sorry, teacher, are you writing?
Oh, yes. So again, it's not working. And the third one is this, while var is different from 0, do something inside. And that's it. We will have just 3 different instructions. And from here, we will see that we can create a lot of all the programs we can imagine. So, well, this is, I think this is surprising because it looks so simple. However, it is not. So, for example, we don't even have instruction for clearing a variable. By clearing, I mean setting it to 0. So we can define a new program that will be named clear, and it will have as argument a variable. And we can define it by using a colon, just like in Python. Well, of course, you can use a different notation if you want, but we can define this program that will be called clear. And what it will do is, while the name of a variable is different to 0, then just decrement its value. And that's it. So with this simple program, we are using the basic blocks, which in this case are these 3. We are using these basic blocks to create a new program, which will be clear. And as always, you know, this course is always constructing and playing with blocks, just like Legos, or maybe some of you had Tente, I don't think so, or Exin, or I'm going to hold. Does any of you have Tente? No. Exin? No. Okay, but you know Lego, right? Okay, so we are building like using Lego blocks construction. So we are doing the same again, but this time these are our basic blocks, our very, very basic blocks. And with this, we create a new tool, and this will be clear. And of course, we need a way of assigning a new, the value of a variable to another one. So we will create var1, sorry. Uno is in Spanish, it's 1. So we want to assign the value of var2 to var1, and we will use this notation. So I will skip this, triangular braces, because now we are speaking about particular variables, but of course we can change them with anything we need. So the program for assigning the value of a variable from one to another will consist first of clearing a new variable, which can be called aux. So this is auxiliary variable. And then we do clear var1, and while var2 is different from 0, then we will increase aux and decrement var2, and that's it. And then we will enter another while cycle when we have aux is different to 0, and then we will rebuild the value of these two variables, var1, and increase var2. And finally, we decrease aux, auxiliary variable, just because we need it to reach 0 and then stop. And that's it. So we have defined 2 different programs here. Our first 2 programs, one is clear, another one is assignment. So this looks a little bit like, well, it's too basic. It should be defined as one of the basic instructions here, but no, not even assignment is a basic instruction of this language. The basic instructions are only these 3. So if you want to see, well, does this really work? Well, let's try it. Let's suppose we want to assign the value var2 equals 3, and let's say bar1 equals something else. We don't care, 5. And then we will see how this program works. We have the initial value of bar1, bar2, and aux. When we start, variable 1 has 5, variable 2 has 3, and aux has something. You can think of anything you want, maybe 8. We don't care. Why we don't care? Because we will start by clearing aux and clearing variable 1. And at that point, we will have 0 and 0. And variable 2 still has number 3. Then it says, while variable 2 is different to 0, increase aux and decrease variable 2. So this means it will increase aux because variable 2 is different to 0. Then we will increase aux to 1 and decrease variable 2 to 2. And that's it. Then we evaluate again. Does variable 2 is different to 0? Yes. Okay, then increase aux and decrease variable 2. And again, last loop, we will check again if variable 2 is different to 0. Yes. And then we will increase aux to 3 and decrease variable 2. And this time, if we check if variable 2 is different to 0, no, then we finish the while loop. Then we start the next loop that says while auxiliary variable is different to 0, which is different to 0, then we increase variable 1, and variable 1 goes from 0 to 1, and then we increase variable 2, which goes also from 0 to 1, and then decrease aux. And to decrease aux is 2. And we check on aux is different to 0, then we loop again, and then we increase variable 1, increase variable 2, and decrease aux. Still aux is different to 0, so we go again, we increase variable 1, increase variable 2, and then decrease aux. Because aux now is equal to 0, then we finish. And then we finish with the same value that we want to copy from variable 2 to variable 1, 3, and 3. And that's it. So it might be a complicated way just to copy the value of some variable to the other. You know, here in this subject, we like to complicate things even for a simple sum for adding up. For addition, we saw the complicated way of adding. So now we are studying the complicated way of assigning a variable value to another variable. But this will pay. And this pays because whenever we do this, then we are guaranteeing that everything that we do is based on these variables, on these initial instructions. So it looks like the initial function, as you remember, 0, projection, successor. It's kind of that way of reasoning. And now we will match both of them. We will try to do the following. Imagine if we can implement the initial functions and if we can implement the different mechanisms of combination, composition, and primitive recursion, and we can implement minimalization, then you know what this means. If we are able to implement those functional mechanisms with these functions, then it means these 3 functions will be the most powerful functions we need, and then we need no more. That's what we are doing. So you see why this is important. Okay, so let's start. We will start by defining the function 0. And the function 0 is handled by clear. So we just need to do some clear. And clear who? So we will now do some standards. So our standards will be that the input will be always given by x1, x2, xm, and the output will be given as z or z's, z1, z2, c2, c3, etc., up to zn. So this is to give or to map a function that goes from m tuple to the n tuples. So you thought you would get rid of these k, m, and n. Well, no, we still are using them. That's why at some point I asked you to pay special attention on these values. And at that point, for example, Dima complied that, well, why do we have to do some positional reasoning on tuples? Well, now this is why it has some logic in it. So in order to see more why input and output have or are working within input X and output Z, then let's consider the successor function. I cannot. The successor function is handled by first copying the input number to the output number. That's it. The input is given by X, and the output will be stored in Z. And what we have to do now is just to increase Z. And that's it. You see, it works, right? So this, if you consider this successor function that has some X and it will yield something like a Z, you can regard it something like this. But this is abusing notation, so I will erase it so that I don't get blamed afterwards for misusing mathematical notation, which I think sometimes I do, but well, don't tell anyone. Okay, so finally, the projection function that we have defined previously, well, it's pretty easy, because what we want is just to return as the first element the J, how to say, X, the jth element. Yes, so we have the element number J, which is this one, and then we just return it as the first element. It's just a copy, and that's it. So you can see that projection can be defined very easily in terms of this basic programming language or bare bones programming language. So that's it. So far, we have been able to implement our initial functions in this basic programming language. Okay, now we have to show that we are able to implement all the mechanisms for creating the partial functions. So we will consider two partial functions, one going from K and going to M, and we will consider a different function which goes from a K tuple to a N tuple. Remember that whenever we use this, these are tuples, you know this already. And then if we want to compute F cross G, then the only thing we need to do is to execute the first program and then execute the second program and then store its results. We move them, move the results to the latter part. So let me see if there is an example here. Remember that this, when we are using this operator, it means that the output is concatenated. So the output of F will go first. So the first M elements are the output of G, and then I will use a different color. And then the elements of, oh my God, of G are given here. And this is just by position, and these are N elements. Yes, remember that this operator that is composition, yes, composition, it will give you the results of G move to this part and the results of F move to this part. So you can imagine, or you can think of a program that is called G. And this program then, after it's executed, will move all of its outputs. For example, let's say that G has N outputs, and you have to shift them by M positions, meaning that the output that remember that we are obtaining all outputs as Z, yes? Then the Z1 must be moved to the m+1 position. Why m? Because we need to make space for the result of f. So we shift, when we first execute G, the result of G will be given as Z1, Z2, Z3, etc., up to Zn, right? So we have n values for the output of G. So we will take, you can see, imagine that this is here, 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 so we need to shift them. In order to shift them, we just add m numbers to them so that they are moved. So that's why this output, which was Z1, now will be moved by m positions to the right so that it gets here. So this will be position Zm+1, Zm+2, Zm+3, etc., until reaching m+n. And then we have free these positions. We have this position free, and then we can use them. So let me just write this. We have to move one by one. Z2 is moved to Zm+2, and finally m+n until we reach n. So by this fragment of the program, what we are doing is moving the outputs of this to the right. It's that simple, no more. And when we have moved them, then we are able to execute F. And then when we execute F, then automatically we will have these values filled. Z1, let me put with red, just to keep with the colors. So we will have Z1, Z2, until Zm. And this is the output of F, while the blue one will be the output of G. And just by using this program, then we are calculating F cross G. Yes, because remember, cross is just putting the result of one function after the other one. If you remember, you can say, for example, the, what we can say, 0, and then we combine it by the projection of the second element of the 3 tuple, which is 5, 8, 3. So when we combine this, we will have 0, 8. So the first one, the first part will be 0, and the second part will be 8. When we compute this, we only move it to the right, we shift it by one position, and then we calculate this 0. Yes? This should be understood like 100%, because if not, it will get a little bit more complicated afterwards. But we are just moving them. And then we calculate G. Then we move the results to the right. And then we leave this space free so that we can calculate F. And at the end, we have a single vector with the first part being the result of F and the second part being the result of G. And that's it, because this is what this mechanism does. No more, it's no more complication with this. Okay, so now let's see the second mechanism, which is composition. So let me change here. So we will have two functions just to review composition, which is G is composed by F, and it consists of an L tuple and a G, which takes this L tuple as input and gives an M tuple as output. And therefore, G composed by F will go from a K tuple to an M tuple. Yes, so we have seen this already, and this is because we are taking as input this K, and then we will take it as an M. Okay, so in order to do this, then we first calculate F. So to calculate F, we will have a program that is F. And then the outputs of F will become the inputs of G. In order to do so, if we have, in this case, L outputs of F, then we have to move to the input number 1, the output number 1. So this is, not to confuse you, this is the output of F will become the input of G. So we must do this for all the outputs of F, which are exactly L. Why do we have L outputs of F? Well, because we know it's an L tuple. And why we know it's compatible with G? Because G has the same L tuple as input. Therefore, we will copy L times, or we will copy for the L outputs, we'll move to the input. And then we just execute G. And G will take the input of F, and it will output, it will yield the, just to put it here, it will give you Z1, Z2, until Zm as answer. And that's it. So you see the composition mechanism can be very easily implemented by using the functions we already know. That's it. Now the third mechanism we saw is recursive, primitive recursion. So we will see it now. So far, how are we going? Fine? Or so-so? Okay, thanks. Okay, so remember that recursive primitive recursion had a template that was very fixed. So we have the basic case being this, and then the following cases being calculated based on the previous case, like this. So we have three functions. We have h of x, which is a tuple. In this case, it will be a k tuple, a y, and we will invoke again this f with the previous value of y. This, we have already seen this. So now we will, let me write the size of the tuples. We have here that there is a function called g, which takes as input a k tuple and returns an m tuple. While in turn, h will take as input a k plus m plus 1 tuple and return an m tuple. And finally, f, we will take a k plus 1 tuple and return an m tuple. So first of all of them return the same m tuple. And this k plus 1, remember that this plus 1 is because we have k elements here. So k elements, k tuple, and this will be plus 1. The same here, we have k elements because this x is a k tuple, and then it will take plus 1 element. And because this has no plus 1, so G only takes a k tuple as input. You can see it here. And the result for all of them is m, m, m. For h, we have k plus 1 plus m, because f will return an m. So if you want to draw it here, we have here, this is k, this is plus 1, and this is plus m, because f will have as output m elements. So h will take as input k plus 1 plus m, k plus y plus m plus 1. And this y is the number 1. So as I told you before, maybe it's easier for you to remember, but it's a bit weird, but it's easier for you to remember if we have k plus 1 plus m, just to keep the order in it. Okay, now that we have this, then we will implement primitive recursion by using our basic programming language. So first of all, we calculate G. Why? Because it's the basic case, the lower, the bottom case. And then we will use some auxiliary variable where we will temporarily store x k plus 1. So before I tell you, I want you to tell me who is k plus 1. Here, who is k plus 1? Remember, this will be the first k elements, x1, x2, x3. And then when it finishes after xk, we have or maybe I can write here with a different color. You can see this as an input tuple, x1, x2, x3, xk, and then you will have xk plus 1. So these first ones map to k, and this one maps to, in this case, 0, yes, Oscar. But in general, it will map to y, right? So whenever we say here xk plus 1, we are talking about y. Why don't I say y? Why do I say xk plus 1 instead of saying y? Well, because remember that we are using, our variables are only on the domain of, not the domain of, the name of our variables are only x for input variables and z or z for output variables. That's it. That's why we don't use y. Of course, we could use y, but this positional system allows us to know that within this tuple, because we are seeing this just a very, very large tuple, this is also a very, very large tuple, we are just accessing them by positional value. Okay, so this is y. Okay, so then we will erase y. We say clear xk plus 1. If you want, we can put it like this in green so that you remember that this is y. And then our while auxiliary value, which was y, is different to 0, we will do the following. We will put as input as xk plus 2 the output of g. And then we will copy all these values until we reach k plus m plus 1. And I would say again, k plus 1 plus m. It's easier to understand. And zm. So maybe at this point you say, why the hell is the teacher doing this? Well, because this is the last class and this is the last time I can make you suffer. So that's why. Okay, so this is Z1. This is the output of the previously calculated G. We have not overwritten it. So this is the previous output of G. And this is the second previous output of G. And this is the mth previous output of G. Remember that G has exactly m outputs and no more, no less, because it's the definition of G. Yes, m can be 1, m can be 2, and can be any number, but in general terms, we have m outputs. So we are copying them into xk plus 2. Why plus 2? Well, because we have not seen yet, but what we want to do is to invoke h, the function h. And the function h will take as input first k elements, which is x1, and let me use different color, which is x1, x2, xk, and these will correspond to x. Then in green, because we said that y would be green, then we have x, really green. Then we have x to green. xk plus 1. This is this y, yes? And then finally, we will have m elements, xk plus 2, xk plus 3, until reaching xk plus 1 plus m. Why? Because f has m elements. Yes. So when we copy z1, z1, z2, zm into these ones, because we are preparing the input of h. The input of h will consist of k elements, then the number of y, and then all of this. And how do why I know I'm feeding the correct y here? Because at every point we are using this is y, and we have never, well, we have destroyed it, sorry, we have destroyed with 0. So the first time I'm feeding this value of y with 0. So I'm saying I'm trying to calculate after the basic case, I am feeding this value. And then I will increase, for calculating the next value, I will do increment x k plus 1 and put it in green so that you remember this is y. And then we will decrease aux. Why do I decrease aux? Because this is my counter. So that if I want to calculate for 3, then I will go back to the basic case 0 and calculate g, and then I will calculate for the remaining cases. In this case, for the basic case, I will return for y equals 0. Yes, in order to calculate for y equal 1. And then I increase y so that next time I will calculate for 1 based on 0, calculate for 2 based on 1, for 3 based on 1, etc. So maybe you want to do an example of this or no, I think you don't want to make an example of this, but we have time, so we will do it. And let's see. Imagine, let's do something simple. Let's do an addition. So you remember, I will compress this. So this is a good algorithm of compression for reusing whiteboard space. So addition was given in terms of H, and you see also why it was important to use this template of F, H, and G, because this way we are able to translate it into this language, for example. So let's see. Addition, as we saw it, was given by, I'm looking for the original definition, here it is. It says plus x comma 0. So the G is given by the projection of the first number of the K tuple. In this case, our K tuple, the value of K is 1. And then we calculate the following value, which would be for y plus 1 equals to the successor of the projection of the third element of the 3 tuple from x, y, and plus x comma y. That's it. So now let's define each of them in our basic language, which is G. And G is defined as, let's use some colors. So this is G. So G will be defined as the first element of the one tuple. So this will be Z1. Yes. And that's it. Then if we define F, no, then we define H, and H will be the successor of the third element of the 3 tuple of the previous element. So in this case, this number will be F, and it will be defined in terms of the previous one. Let me think a little bit on this. Mm-hmm. Okay, so this is I'm not sure if we need to execute F here. I think it shouldn't be necessary. Because we don't need stacking. So let me just think a little bit on it. Yes, so we will have first the projection of this element. Remember that we have here, this will be the first K element, so this will be X1 and K equals 1, so that's it. So we will have here X2, which is Xk plus 1, and then we will have this as X3, and this will be Xk plus 1 plus M. And in this case, M equals 1. So we will return the third element, which in this case is Z, which is X3. And then we need to do the successor. So remember that for this, we did increase Z1. And that's it. So I wonder if this will work. Let's try it. I think something's missing, but let's try it. It looks so simple, but maybe it will work. So let's try to add up 5 and 3 as before. Let's say we want to calculate the addition plus of 5 and 3. So in this case, we will have our X1, X2, and Z1. X1 is 5, X2 is 3, and we will use also an auxiliary variable. Our primitive recursion says we will execute here and we execute G. And G says copy X1 to C1. So we copy X1 to C1. C now has a value of 5. And then our algorithm says the value of X K plus 1, which in this case is X2, which in this case is 3, store it into aux. So aux will have the value of 3. Okay, the next one says clear Xk plus 1, which in this case is X2. So following the colors, it should be this one. And then it says clear this one. Okay, 0. Then while auxiliary is different to 0, then copy for each one of the M elements, which in this case, M is equal to 1. M equals 1. So we will do it just once here. Sorry, we'll just once. So we will copy the output of Z1, which is 5. We will copy to Xk plus 2. K is 1. So we will copy this to X3. Yes, so I need to consider X3. Let me move this. Okay, so we have X3. So far we haven't used X3, so we will move the value of X1 to X3. So now X3 is the same value of X1. And because M is just one element, then we don't need to do all of them. Now we will execute H. H says, copy the value of x3 to z1. Okay, it was already there, but then let's recopy it. And then increase z1. So now z1 will be 6. And that's it. Finish h and then increase y. Our y now is 0. Remember that xk plus 1 is this one. So now we increase this and its value is 1. And decrement aux, the auxiliary variable is 2. Okay, so sorry, I need to compress even more the whiteboard because we are running out of space. Okay, that's extreme compression. And I will shift this upwards. I insist, this is very nice. I don't know how will I do it when I don't have this sort of magic. Okay, so we have decremented aux. Then we evaluate. Aux is different to 0? No, then we still execute. And then we have z1, which is 6, and then we move to xk plus 2. Xk plus 2, remember that k is 1, so xk plus 2 is 3. If you need some colors to remember, then let's say xk plus 2, in this case is x3. Okay, so we have numbers to remember, colors to remember. So we move this value of z1, which is now 6, we move to xk plus 2. And that's it. Then we execute h. H says, copy, let me project again. I don't know what happened. Sorry for that. Oh, so sad, I cannot. Don't say it, restart your device, it says. Last try. Wow, it recovered. Thank you for your good vibrations. Okay, so we have so far, now we restarted, we copied to this and we were executing H. In order to execute H, then we have X3 move to, copy to Z1. X3 copy to C1 and then increase Z1, which now is 7. And then we leave H and then we increase xk plus 1, which is y. So this will be 2. And decrement aux. Aux now will be 1. And then we ask, is aux different to 0? No. Then we loop again. And then we copy z1 into x3. So we copy z1 into x3. Now it's 7. This is very old. Now it is 7. And only for m elements, m, remember, is equal to 1. So now execute h. H says copy x3 to z1. Copy x3 to c1, and then increase z1. That's it. Then we come back from h, and then we increase y. We increase y to 3, and then decrement aux. Aux now is equal to 0. And because it's equal to 0, we have finished. So our result is given, not yet. I think I missed something. Give me a second. We are almost reaching. And no, it's okay, it's okay. And then we have our result. Yes, thank you. Our result is Z1, 8. So we have properly calculated plus of 5,3 equals 8. You see? So, well, if you thought that that recursive functions were very difficult or were a complicated way, then try to calculate them by using non-recursion. So you see, it's a bit crazy, but what we are trying to point is that we are able to calculate the primitive recursion by using the same elements we have using for our very simple programming language. Can you hear me properly? Because I see you moving slowly. Okay, thank you. Well, now you may say, how come this is cheating? Because you are using the stack for calling subprograms here, subroutines. And no, I can tell you, no, I'm not cheating, because you can copy this, you can copy it here, and you can copy the program for H, you can just copy it here. You don't need stacks to calculate recursion. You see, that's why primitive recursion is different from general recursion, because as you can see here, you don't need stacks to calculate primitive recursion. You see, it's a bit strange, right? Because we are taught always that for calculating recursive functions, we need a stack forcefully. And then we see here, no, there's no stack. Just calculate the basic or the base, the bottom case, and then from there build up. No need for a stack. So that's a bit surprising, but it works. I just did an example here, which if we try to do a different example, then you will see it gets more complicated, but I just want you to grasp the general idea, okay? Well, sorry for complicating your life again, but there is just one last mechanism that is missing for being written in this simple language. And that's primitive, no, that's minimalization. Okay, so let's change page. Minimalization can be calculated in a very simple way. We can do clear x k plus 1. And just to remember who is k plus 1, y, the same as before. Then we will execute some g, and then we will do while z1, this is the output of g, is different from 0, do increase g, and then execute again g. And that's it. If you find the 0, then just return x k plus 1. So this is g and this is g. And if not, then you will loop endlessly here, meaning that it's undefined. So very similar to Turing machines, in this case, undefined means that you never return a value. So remember, we have as minimalization, we have the minimum g for which certain function called g equals 0. So again, as before, if you regard this x, this is expanded to x1, x2, until xk. And of course, this y will be xk plus 1. So now you are very used to this, so no problem for this. Then what you do again is clear y. So we start looking from y equals 0. Then we execute the function g, which is defined somewhere as we want. And then we try, if the output of this g, remember that the outputs are giving us z's. So if the output is different from 0, because we are looking for 0, then we increase the value of g. Then try for 0, for 1, for 2, for 3, and execute g again. If we find the output equals 0, then return the minimum y for this value. So if we examine for the division, for example, which is the only function we have seen so far. There are many more, but we only saw division here. Let's try to do the exercise. We have division defined as the minimum t for which x plus 1 minus mult. We have seen this already, so this is just to practice here. So maybe I won't try to define g in terms of this. You can, as the book says, the exercise is left to the reader. So this is a very convenient way to say we will not cover it here, but you can do it really. So this will be g.
Sorry to interrupt you, doctor, but your screen is not updating.
My screen is mean. Okay, sorry. So this is division, and this will be g. Thank you for telling me. And then in this case, t will be a third variable. So this is why it is important to count how many. This will be x1, this will be x2, and this will be x3. So this is xk plus 1. So in this case, we have this as our green friend. This is here, it's not called y, you see. Then we start calculating this. We say, okay, clear t. So by saying we have x1, x2, x3, and we have, of course, the output. So at the beginning, we are trying, if we want to do this exercise with divide 5 by 2, as we did before, then the value of x1 is 5, the value of x2 is 2, and the value of x3 is we don't know, and we don't care now, and the output is not, it can be defined, but we don't care. So we start with clear x plus 1. And remember that our x plus 1 now is x3. So clear this, and now it has the value of 0. Then we execute g, and g says x plus 1, x, in this case, our x will be x1, and y, this is x3, and y is x2 and x2. So x1 is 5, 5 plus 1, 6 for our example. So now we have 6 minus, and we have this is x3 is 0 multiplied by 2, well, it's 0 plus 2 is only 2. 6 minus 2 is equal 4. So g, after executing g, z1 is 4. And then it asks, is it different to 0? Yes. Then increase xk plus 1. So we will increase, we will increase this one. And then we execute again. We will have x1 equals 5. So again, we have 6 here, and minus x3 is equal 1. Here equal 1 multiplied by y is 2. So it's 2 plus x2 is 2. So we have 2 plus 2. We have 4. 6 minus 4 equals 2. So now we have all our results here. So z1 is 2. And we are executing this one. Is z1 equal 0? No, then increase xk plus 1, which in case is x3. So this is 2. And execute g. Execute g. We have not defined g in very detailed way, but we are executing it here. So now we have 6 minus, and we have x3. Now the value of x3 is 2. 2 times x2 is 2 times 2 is 4 plus x2. So this is 6. 6 minus 6. So this is equal 0. So now after finishing execution of g, z1 equals 0. then we comply with this condition because z1 equals 0, then we stop, and then finally we return this x plus 1, which is this one, we copy it into the output. So the output of this is 2, meaning that the answer of the division is 2, which is correct, as you remember. Okay, so far we have shown that we are able to implement in our very, very basic or simple language, we are able to implement all the mechanisms here, shown here. So we have started by defining the initial functions. We have defined these mechanisms and including, where is it? Minimalization here. We have defined 1, 2, 3, and 4 mechanisms. So now we can say we can reach all computable functions by using our simple, very simple programming language. And remember that our programming language started just by these 3 simple instructions. So next time you walk into a bar, you can talk with the pretty lady or pretty boy next to you and tell him, do you know how many instructions the very simplest programming language has? And he will say, no clue, or she would say, no clue. You can say 3. And then you can start talking about this. Maybe we should put this into YouTube so that you can show the video, or you can do your own video. And you will say you will have success in that pickup line. Okay, well, jokes aside, you can see this is very important because we are used to think that the more instructions a language has, the more powerful it is, right? But talking about computing power or the power of computing results that we need only 3 instructions. And I think that's surprising. Well, the first time I saw this, I was shocked, like the meme that says like, exploding head. Because it's too simple. How come all the power of computing power in the universe is started just by these 3 instructions? And of course, it has also a lot of implications. There are variants. These are not the only basic building blocks. Sometimes instead of having a while, you can have a for, or different things. If you want to explore this, you can do exercise. This is not homework, but if you are interested in this, you can do exercise number. There is an exercise here. Give me a second. Aha. Exercise number 1 on page 233. Exercise number 1, page 233, of course, of the English version. And it has a loop instruction. It has clear, increase, and loop. And from there, you can build again all the other things. So it has not increase, decrease, and while. So it says clear, increase, and loop. Loop the variable, and you say how many times. You see, it's really different, but it's also interesting that with this, you can create all the power again, but with different ways of constructing it. So it would be interesting, well, of course, if you are interested, but that you try to build all the initial functions, all the primitive recursive functions, and also the partial recursive functions by using these 3 instructions. So, well, that's it. So, tell me, what do you think? So this is the content of thoughts. After...
We are speechless.
Okay. Well,
mind-blowing.
Well, I hope you enjoyed this. This last part, well, I enjoy, of course, all the course. I hope you enjoyed it as well. But this last part, I think, is very interesting because it has a lot of implications, because I think all of us are programmers and we are using lots of programming languages, even Java. But and it results, all of them have the greatest power for programming. Well, of course, if we talk about expressiveness, maybe you need object-oriented programming, maybe you need functional programming, maybe you will need other things, right? I'm not saying that all those beautiful and nice things are not needed. However, you can always go back to very simple instructions. And also there is a part that I'm not covering in this course that of course can be helpful to you, and is the fact that you can do the same as we did with our simple programming language with Turing machines. And then you demonstrate that the initial functions, the primitive recursive functions, and the partial recursive functions can be implemented in a Turing machine, and vice versa, that you can implement a Turing machine by using primitive functions. This is interesting because if you show in one way and then you show into the other way, then you are demonstrating that both theories are equivalent. And this is done, also in Berkshire. If you are interested, you can see also the last part of the chapter. So we don't see it here because of time restrictions. You can see we are finishing on the edge of the time. So we have to finish this course. However, I think all those things are interesting. And well, just to finish, may I invite you to the next course we will be giving. The next, well, of course, it's not so technical or so theoretical maybe, but if you enjoyed the talk about the Godu machine and things like that, like make you think in some sort of philosophical ways, I will be lecturing artificial intelligence and society. Probably it will be in Spanish only. I don't know yet, but well, but anyway, I want to invite you. Well, so I couldn't avoid the commercial at the last part. So as always, well, I always thank you for your attention at the end of each class. But well, this is the final thanks. And also thank you for being such a nice group. Thank you for participating, for submitting your homeworks, for giving nice ideas. And well, if there is something you want to add to this course, well, this is the time. If you don't want, don't worry. And well, this is all from my part. I will shut up now.
I think we would like to thank you for this course and